To develop high-performance distributed applications, it is important to understand the underlying architecture, its components, and how they operate. In this lesson, we will look at how DAML applications operate under the hood and also learn about the components in the DAML ecosystem that enable them to span multiple parties and networks while ensuring data sovereignty, privacy, and synchronization. Let us start with a simple scenario in which multiple parties need to interact with each other in a business transaction. Let us say that there are two manufacturers, A and B, manufacturing widgets, and two shipping companies, C and D, providing shipping services to A and B. There are three important considerations to keep in mind when designing a system for these companies to engage in business transactions. First is trust. A and B, being competitors, do not trust each other. The same applies to C and D. Organizations do not want their data to be visible to their competitors, but they do need to share some data selectively to carry out business transactions. A should be able to share its inventory data with C and D without worrying about B having access to that information. Similarly, C should be able to get business from A and B without worrying about D being able to see its business transactions. Data generated from this crisscross of relationships should not be exposed to competitors, as it can result in loss of business and legal challenges. This lack of trust, in turn, means that organizations want to have complete control over their data and also limit visibility into it to protect privacy. The second important consideration is reconciliation. For example, let's say A shipped 100 units of a product using C, but due to some shipment issues, C could deliver only 95 units at the destination. This gap needs to be reconciled to make sure that all books balance out correctly, and this reconciliation, because of its scale and complexity, needs to be automated. For automating such business transactions that cross organizational boundaries, traditional architecture uses multiple point-to-point communication networks. Those networks process messages concurrently, with each organization keeping its local data store with full data ownership. This distributed architecture approach leads to two types of problems. The first type is messages getting out of order due to inherent network delays, message drops, duplicate messages, out-of-sync clocks, network outages, and so on. The second type of problem is the interpretation of messages. The messages are generated from a variety of platforms, so they need to be correctly interpreted and ingested into the destination systems. Any changes in the message format or errors in interpretation logic lead to communication breakdowns. Handling such breakdowns requires manual intervention and troubleshooting, which often requires coordination and collaboration across multiple organizations. This leads to delays and loss of productivity. One solution to this problem is to use blockchain as the backend, where the data across all the organizations is stored. This solution removes the hassles of point-to-point communication. However, this architecture introduces two problems. The first problem is that the blockchain by itself offers little to no privacy because every party can see every transaction, all the data, and its metadata. This breaks the consideration of trust because organizations competing against each other cannot work with this kind of architecture. The second problem is the loss of data sovereignty. All companies want to control their own IT systems and data. With traditional blockchain, they give up that sovereignty. It also means that if an organization needs to delete some historical data due to regulations such as GDPR, it cannot do that unilaterally because there are multiple copies of the entire data across the network with all the parties. This is where the Canton distributed ledger solution comes in. At a high level, its solution is twofold. First, each organization can own its data in a local data storage. No other organization has access to this local data store. This data store keeps a record of all the smart contracts in which the organization is involved. It is called the Private Contract Store, or PCS. These independent data stores across the network make up what is called a virtual global ledger. Individual organizations can only keep those parts of the ledger for which they are authorized. This takes care of data sovereignty and privacy. A PCS is part of a bigger Canton component called a participant node. A participant node is a server through which the users of an organization can access the organization's PCS. It is important to note that the smart contracts stored on a PCS are visible only to those parties that are registered on its node, and their access is controlled according to their authority and privacy rights. A participant node houses the DAML archive files, or DAR files. DAR files are generated from the DAML code that models business logic and process workflows. A participant node handles authentication, transaction validation, and many other services required for a DAML application to function. In this way, participant nodes address the need for data sovereignty and privacy by controlling access to the ledger. For synchronization, participant nodes use the synchronization layer. The synchronization layer is a guaranteed total order multicast system that ensures consistency of message ordering and delivery between participant nodes. It resolves the reconciliation problem and also offers some other identity and transaction coordination services. This layer can run on a traditional SQL-based system, such as Oracle or Postgres, or on a blockchain platform, such as Hyperledger Fabric or Besu. Distributed ledgers achieve this consistency by using a consensus protocol, and the Canton Distributed Ledger Solution provides its own consensus mechanism, which is called the Canton Protocol. You can think of a consensus protocol as an algorithm that is followed by all the nodes in a decentralized network to ensure agreement, trust, and security. The Canton Protocol makes sure that all smart contracts related to a business transaction stored in a database are either updated completely or, if there is any problem, the entire transaction is aborted. This all or none guarantee provided by the Canton Protocol avoids the reconciliation problem. So now there is a solution that takes care of the trust and privacy issue by having each organization keep its data in a local data storage, and reconciliation issue by providing high consistency guarantees on messaging and transaction coordination through a synchronization layer. Let us now zoom into the synchronization layer to see how it works. At an abstract level, a participant node connects to a sync domain that facilitates synchronization of transactions. A sync domain has one or more sequencers that establish the total order of messages and implement a total order multicast. It also ensures that only relevant messages are sent to the participant nodes, which further strengthens privacy and enables scaling. A sync domain also has one or more mediators that coordinate transaction commits across multiple parties, ensuring privacy and atomicity of each transaction. Let us summarize what we have learned so far. The point-to-point network communication channels used by organizations to carry out multi-party transactions are fraught with technical problems related to the network, as well as problems related to message interpretation. These problems require manual intervention and lead to reconciliation issues that are hard and expensive to resolve. The blockchain technology used in its raw form offers a synchronized data layer resolving the reconciliation challenge, but it takes away data sovereignty and privacy, which are critical for organizations to function in a competitive market setting. The Canton Distributed Ledger Solution resolves these challenges by offering a solution that, at a high level, has two parts. First, each organization keeps its own local data store, which enables privacy and data sovereignty. And second, all organizations connect to an underlying synchronization layer that ensures consistency of data across the network and resolves the reconciliation issue by a consensus mechanism called the Canton Protocol. The underlying network of Canton distributed ledger solution is called the Canton network and has the following key components. First, participant node, where the DAML application in the form of DAR files and the smart contract ledger called Canton ledger or DAML ledger reside. This is where parties are hosted and given access to smart contracts. And second, sync domain, which serves as the synchronization layer. It has one or more sequencers, which ensure total ordering of messages, and a mediator, which ensures atomicity of business transactions.